Bonjour tout le monde. Bienvenue à cet événement spécial dans le cadre du Colloque des sciences mathématiques du Québec pour écouter les travaux du récipiendaire du prix Aisenstadt 2020, Robert Haslhofer de l'Université de Toronto. Avant de présenter notre récipiendaire, en fait, il y en a deux cette année. C'est exceptionnel. En fait, ça arrive très peu souvent. On va avoir un autre exposé dans quelques semaines de Igor Huisken de l'Université de Montréal. Mais aujourd'hui, c'est Robert Haslhofer qui va parler. Donc, avant de présenter professeur Haslhofer, je vais en fait brièvement décrire le prix. Et par la suite, je vais introduire le conférencier. D'accord? Donc, le prix de mathématiques André Aisenstadt vise à reconnaître le talent de jeunes mathématiciens canadiens. Ce prix, comprenant une bourse en argent ainsi qu'une médaille, souligne des résultats exceptionnels de recherche réalisés par un jeune mathématicien ou mathématicienne canadien. Le lauréat est choisi par le Comité scientifique international du CRM et pour être éligible, doit avoir terminé son doctorat depuis 7 ans au moins. Le lauréat est invité à prononcer une conférence au CRM et à présenter un résumé de ses travaux pour publication dans le bulletin du CRM. Hello everyone, welcome to this special event in the context of the Colloque des sciences mathématiques du Québec. Today we have the pleasure to have one of the two recipients of the 2020 Aisenstadt Prize. So before introducing the winner of this year, Robert Haslhofer from University of Toronto, I will briefly describe the prize. So the André Aisenstadt Prize celebrates outstanding research achievement by a young Canadian mathematician and consists of a monetary award and a medal. The recipient is chosen by the CRM's International Scientific Advisory Committee, and to be eligible must be no more than 7 years from his PhD. The recipient is invited to deliver a lecture at the CRM and to write a brief article on his or her work for publication in the bulletin of the CRM. So without any further delay, I'm going to introduce with great pleasure our 2020 winner of the André Aisenstadt Prize. So Robert Haslhofer is a mathematician currently working as an assistant professor in the Department of Mathematics at the University of Toronto. He obtained his PhD in 2012 at the Swiss Federal Institute of Technology in Zurich. Haslhofer then was a current instructor at the Courant Institute of Mathematical Sciences. Since 2015, he has been working as an assistant professor at the University of Toronto. His research interests are centered around geometric analysis, differential geometry, partial differential equations, calculus of variation, stochastic analysis, general relativity. His research is currently supported by NSERC Discovery Grant and a Sloan Research Fellowship. And let me just finish this introduction by mentioning a slight part of the nomination letter. So Haslhofer is a remarkably strong and creative young mathematician working in the area of geometric analysis and geometric flows, including mean curvature flow and Ricci flow. Having completed his PhD in 2012, he has a string of impressive results and is already widely regarded as the leading mathematician in this hot area. This is evident from his prolific publication record and his support that his research attracts. He's much in demand as a speaker, having given more than 100 invited lectures, many at leading institutions. And he is a vibrant and inspiring presence, both in his home department and in the geometric analysis community internationally. So without any further delay, it is my pleasure to introduce to you our 2020 Aisenstadt Prize winner. And please, Robert, the floor is all yours.
Thank you so much for the kind introduction, and I'm very honored to receive the Aisenstadt Prize. And also thank you all for coming to my talk. So I'm going to tell you about mean curvature flows through neck-singularities. So the last part of the talk, which gives you a glimpse of the new results, is joined with Kayong Choi and or Hershkovitz in dimension 2, and with Choi, Hershkovitz, and Brian White in dimension larger than 3. But most of the talk will just be some general overview of what is mean curvature flow. So mean curvature flow is an evolution equation for surfaces. So you have some surface here, and then as time evolves, the surface evolves as indicated in the pictures. So that So the equation actually first arose in material science in the 1920s as a model for some evolving interfaces. And over like approximately the last 40 years, it has been studied very actively, both in pure math and also in applied math, actually. And so here the picture shows what the talk will eventually be about. So that's a picture of a mean curvature flow of surfaces that flows through this neck singularity here. But to get started, let's just start with one-dimensional mean curvature flow, which is curve shortening flow. All right, and I should have told you, please ask many questions, so otherwise it feels like talking to a black hole, so please ask questions. Good, okay. So curve shortening flow that goes as follows. So this blue thing is a one-dimensional curve in the plane. And at each point on the curve, there's some curvature vector indicated in green. And then we deform this curve in time. And the equation is just at each point on the curve, the velocity is given by the curvature vector at that point. So if you do this, then you get a one-parameter family of curves. So here, maybe that's how the curve looks at time equals 0, and that's how it looks at time equals 1, time equals 2, and so on. Good. Okay, so let me remind you about some basic geometry. So if you have some curve in the plane, parameterized by arc length s, then if you compute the first derivative, you get the tangent vector t. And if you compute the second derivative, you get the curvature vector k. And since we're parameterized by arc length, the tangent vector has constant unit length. And so therefore, its rate of change is always perpendicular to itself. So meaning we can write the curvature vector as some number k times the inward unit normal n. So all the information about the curvature is contained in this number k. I just have to tell you what is this number k in some easy examples. So curvature scales like 1 over distance. So if you have a circle of radius r, then the curvature is equal to 1 over r. So meaning a large circle has small curvature and a small circle has large curvature. Good. Okay, so that's geometry 101. And then we also have another reminder about PDE 101. So my favorite partial differential equation for some function which just depends on x and t is the heat equation. So the time derivative of u is equal to the second spatial derivative of u. And the heat equation has many nice properties. So it starts with some initial function and then it makes it nicer and more homogeneous. So like if you think about your physical intuition, well, if you have some heat distribution, then it's maybe hot here and cold somewhere here, but then the hot stuff flows to the colder parts and it gets balanced out. So in particular, the solution always becomes immediately smooth and the maximum is always decreasing in time and the minimum is always increasing in time. So here would be a simple illustration. So at the initial time, maybe the function looks like this zigzag function. Okay, and just at the minimum, the second derivative is positive. So d2x is positive at the minimum. So therefore that goes up in time, and at the maximum there, just by the calculus second derivative test, the second derivative would be negative, so that goes down in time. So those things are really easy to prove. That's just a calculus second derivative test, and then it works very well. Even if you start with something which is not smooth and has corners, then it actually becomes immediately smooth. So that's what the heat equation is doing, and the curve shortening flow is kind of a geometric heat equation. So we just learned the curvature is given by the second derivative of the curve with respect to arc length. So it really looks like a heat equation. So maybe the way I wrote it is a bit misleading because I wrote it in terms of arc length s, which depends on a nonlinear way on x and t. So actually it's a nonlinear PD, but it's still this heat type equation. And so motivated by this physical intuition of heat flow, we hope when we start with any initial curve possibly quite wide, but then the heat flow will deform it into a nicer, more homogeneous curve to some nice optimal limit. And indeed, this works amazingly well. So there's a really beautiful theorem by Matt Grayson from 87. So he proved when you have any closed embedded curve in the plane, then under curve shortening flow, it always becomes round and shrinks to a round point. So, okay. So maybe I don't click here because then I mess up my slides. But when you have a moment afterwards, just go to YouTube and Google Grayson theorem, and then you can see some nice animations how this looks. And it's quite an amazing theorem, because you can have a curve in the plane which like spirals around 1,000,000 times, but then the theorem tells you this curve always unwinds itself quicker than it shrinks to a point, and it always unwinds itself quickly enough, and then it becomes round. Good. Okay. Any questions so far? Good. Okay. So let me talk a little bit about applications. So I mean, of course, curves in the plane are quite simple. So those are applications you could also prove without curve shortening flow, but just for the sake of illustrating how the curve shortening flow can be used to something, well, to prove something which is not about the flow itself. Well, first of all, you can use it to prove the isoparametric inequality. So, you know, in the plane, if you have your closed embedded curve, the length squared is always bigger or equal than 4 pi times the area, with equality if and only if you have a round circle. And of course, there are easier ways to prove it, but with curve shortening flow, you can prove it in a line just by observing that this isoparametric difference is actually monotone under the flow. And so then for time approaching the singular time, it converges to the round circle, so it becomes an equality. So therefore, at earlier times, the inequality must hold. Good. Another nice little application is a proof of Smale theorem. So Smale proved that the diffeomorphism group of the two-sphere deformation retracts to the group of rotations SO3. And so this topological statement is actually equivalent. So that's an easy topology exercise that's equivalent to some other topological statement, which says that the moduli space of all embedded curves in the plane is contractible. And that's something you can, again, easily prove via curve shortening flow. Just take all those curves and let them flow all at the same time. Then they all just flow to this to this point, which exactly gives the homotopy you want to prove this topological statement. Good. And another application I want to mention is this Lesternich-Schnellmann theorem. So maybe that's a theorem where one indeed needs the curve shortening flow. So this initial proof by Lesternich-Schnellmann had a gap, and that was later fixed by Grayson using curve shortening flow. So the theorem is when you have the two-sphere with an arbitrary Riemannian metric, then you can find always at least 3 embedded closed geodesics. So for example, this number 3 is sharp on certain ellipsoids. So on certain ellipsoids, you exactly have 3 equators, which are the only closed embedded geodesics. And again, you can so geodesics are curves with vanishing curvatures. So that's the curves you get as a limit of time going to infinity of curve shortening flow when you converge to some stationary point. Okay, any questions about this sketch of applications?
I have a very simple question.
Sure.
Alexandre here.
Yeah.
Just wondering if these proofs are simpler than any of these are simpler than the initial proof. Like for the Lesternich-Schnellmann, is it simpler than the initial proof of existence of 3 geodesics?
Well, I think for the Lesternich-Schnellmann, you actually need it because the initial proof had a gap. When for the more theoretic proof, one indeed needs some curve shortening procedure. And so there, curve shortening flow, I think, is the simplest way of doing it. But for example, but of course, for the other two statements, they're much easier proofs. So the other two statements I just put to motivate some applications in higher dimensions. Good, yeah, for example, Smale's theorem. I mean, I think the simplest proof is just to use complex analysis.
Thank you.
Sure, good. Okay. Okay, so but this easy proof here motivates some. So that's kind of my favorite application of mean curvature flow. So there's a fundamental inequality in about the shape of a universe. It's the Penrose inequality. So you know there's the positive mass theorem, which tells you, well, the energy of our universe is always non-negative. But then the more quantitative estimate is the Penrose inequality, which tells you that the mass of any black hole is actually bounded below by the square root of its area divided by 16 pi. So here that picture that should be a black hole. So here this black hole, it's one dimension higher. So that black thing is a two-dimensional sphere, and you have this inequality, and equality is only attained for the rotationally symmetric Schwarzschild black hole. Okay, and so this Penrose inequality was proved by prix and Huisken and using inverse mean curvature flow. So the basic proof strategy is the same as here for the isoparametric inequality with the curve shortening flow. So you take this black hole and you deform it in time. So now, so actually one has to use the inverse flow. So the speed is not the mean curvature, but the inverse mean curvature. So in the mean curvature flow, spheres shrink, but on the inverse mean curvature flow, they expand. So then you just take your black hole and let it flow to infinity. And that infinity is, the universe is asymptotically flat. So that's a perturbation of Euclidean space. So that's easy to compute stuff. So at infinity, you can just check the inequality by some perturbative calculation. And then the miraculous thing that is happening is that this Hawking mass here, so this area times 16 pi minus integral of mean curvature squared, that's actually monotone under mean curvature flow. So you checked it at infinity, and by monotonicity, it also holds at earlier times. So that's one of the coolest applications of mean curvature flow, or inverse mean curvature flow. It proves a fundamental inequality about our universe. Good. Okay, and those other things from before, they also have versions in one dimension higher. So Smale proved it for the diffeomorphism group of the two-sphere, and then he conjectured a similar statement should hold for the three-sphere. That was actually proved by Hatcher using topological methods, but it's kind of an intriguing question. Can we also prove Hatcher's theorem using mean curvature flow? And okay, and also this Listonic-Schnellmann conjecture would be, okay, instead of the two-sphere, take the three-sphere with any metric, then the conjecture would be there should be at least 4 embedded, sorry, there's a typo, there should be at least 4 embedded closed minimal two-spheres. Okay, so the first such again, this would be sharp on certain ellipsoids where you indeed have exactly 4 solutions. So the first such sphere was found by Simon Smith in the 80s using min-max theory. And then recently with Catover, we found a second solution using mean curvature flow, and then the hope would be if one understands mean curvature flow even better, then one could find 4 instead of just 2. And also let me mention, like a very big conjecture in topology is the Schoenflies conjecture, which is a cousin of the smooth 4-dimensional Poincaré conjectures. So they don't quite imply each other, but are very related to each other. So the conjecture is that when you have any embedded 3 sphere in R4, then it should bound a smooth 4-dimensional bowl. And again, that's a conjecture where mean curvature flow could potentially be helpful. So at least under some very simplifying assumptions of low entropy that was recently done using mean curvature flow. Okay, so that's that's a question. Sure.
Is the Schoenflies theorem true in dimension 3?
Yes.
Thank you.
Good. Okay, so that's probably just a quick motivation about applications, so that if you care about geometry and topology, then mean curvature flow can be useful for questions like those. But otherwise, some people also just like flowing things for the sake of flowing things. And yeah, I should have mentioned there's also applications like in more applied things, for example, for computer graphics, image reconstruction. It's often quite useful to use flows to smooth out some image. Good. Okay. Other questions about this glimpse at applications? Good. So for most of the talk, I just want to focus on the flow itself. So the applications, apologies about that, were more just a side remark. So let me now tell you what is mean curvature flow. So given any initial surface M0 in R3, so like this dumbbell here in the picture, or more generally, you could have some n-dimensional surface in Rn+1. We evolve it by the following equation. So dtx is equal to h of x. So you have the surface here, and at each point x on the surface, the velocity is in normal direction, and it's given by the mean curvature vector at that point. And if you do this, then you get a one-parameter family of surfaces, MT. Okay, apologies. I think I forgot the geometry 102 slide. So let me just tell you in words. So the mean curvature vector is some vector which is again normal to the surface. So it's really just some number h times the inverse unit normal, and this number h is like some average curvature. So it's the sum or average of the principal curvatures. So a sphere of radius r would again have just mean curvature equal to 1 over r. Good. Okay, and from the PDE point of view, well, the mean curvature is kind of like the Laplacian of the position vector. So from the PDE point of view, that's again a geometric version of the heat equation. And that was the initial motivation why people wrote it down first, at least from the pure math perspective, because, well, we all like surfaces, and then the hope was, well, take some surface and evolve it under mean curvature flow, and it will evolve towards an optimal surface. Good. Okay, and the subject kind of started with this classical theorem due to Huisken. So probably many of you met Huisken because he's the director of the institute in Oberwolfach. So what he proved in '84 is that if you start with any closed embedded surface that is convex, so if you have this convex initial surface, then the flow works extremely well. So then this convex surface, under the evolution, first of all, it stays convex, and then it actually becomes nicer. So it becomes more and more round, and it also shrinks, and it becomes extinct in finite time, and it converges to a round point. So the meaning of this phrase converges to a round point is, well, if you look here, and if you rescale to unit size and take a limit of those normalized guys, then you indeed get the round sphere with the round metric. Okay, so that was this early landmark result, which kind of got the subject started, because there one can see, well, okay, those geometric flows, they really work very well to deform some arbitrary convex initial surface towards this optimal geometry. And yeah, maybe I should also mention that there was a similar result by Richard Hamilton, not about mean curvature flow, but about Ricci flow. So Richard Hamilton proved if you have a three-dimensional Riemannian metric with positive Ricci curvature, then under Ricci flow it converges to a round metric. So that was some early indication that Ricci flow could be useful to prove the Poincare conjecture. Good. Okay, so that's the convex case. So there's the picture is the nicest possible picture. So you just converge to something round. But of course, convex surfaces we already understand them anyway. So what one really wants to do is, well, start with more general initial surfaces. For example, for the applications I talked about before, well, it's not enough to just understand convex surfaces. You want to understand all surfaces. And then the main thing that is happening when you start with something that is not convex, then most of the time you will encounter singularities. So that's the main difficulty with studying those flows. It's nonlinear equations, and most of the time one hits some singularities. So probably the simplest example of a singularity is this neck pinch singularity example due to Hamilton. So you have some initial surface which has the topology of a sphere, but it has this topology of a dumbbell. Like when you work out at the gym, you have those dumbbell-shaped objects, right? And so what is happening here? So this neck here has mean curvature pointing inwards. So this neck actually shrinks under the evolution. And then after some time, the radius of this neck will go to 0. So that's where you hit the singularity. So there the object is not a smooth surface anymore. The curvature goes to infinity, and this neck pinches off, and it actually breaks your surface into 2 pieces, and then those 2 pieces continue flowing. Okay, so that's how it is when you flow surfaces that are not convex. Most of the time you encounter some singularities, and then much of the research in the last 30 or 40 years was about, well, understanding those singularities, possibly classifying them, and finding ways to continue the flow through them, and hopefully if one understands them well enough, then one can also do these applications I discussed at the beginning. Yeah.
I have a small question. So in this case, it will converge to 2 distinct points?
Yeah, so in that case, there would just be one, in the picture here, there's just one singularity, so it's just one point in space-time where it's singular, and afterwards it's smooth pieces again, and both of them converge to a round point.
If they stay convex, then they will just converge to 1 point each.
Yeah, so from here on, it would be easy. There's 2 convex pieces, so by Huisken theorem, they would converge.
Okay, thank you.
Yeah. Good, thanks for the question. Other questions? Good, okay, so let's see. So the convex case is very well understood. Everything converges just to a round point. In general, we can have singularities. So convex is very well understood. No curvature assumptions is not at all understood. So there's some in-between case which is quite well understood. So that's the so-called mean convex case. So the mean convex case means that everywhere on the surface, the mean curvature points inwards, meaning the whole flow is moving in one direction. Or in other words, if I write the mean curvature vector as this function h times the inward unit normal, then this function h is positive. So and remember this mean curvature h, it was the average of the principal curvatures. So it could be that one principal curvature is negative, but the other one is more positive, so then the average would still be positive. So that's a much weaker assumption than convexity. It just tells you, well, the sum is positive, but not necessarily all the principal curvatures are positive. But in this case, there's still a very well-developed theory. So if it's mean convex, so being mean convex is preserved under the evolution. If it's mean convex, then the flow uniquely evolves through all singularities. And it has a very small singular set. So there's some more precise statements, but for example, when you talk about two-dimensional surfaces, then at almost every time they are completely smooth. And moreover, we know how singularities look like. So all tangent flows are just planes, shrinking spheres, or shrinking cylinders. So for example, in the example before, if you blow up at any regular point, the tangent flow would just be a plane. Here at this singularity, the tangent flow would be a round shrinking cylinder. And here at those two extinction points, the tangent flow would be a round shrinking sphere. Good. Okay, and alternatively, instead of weaker generalized solutions, a more controlled way to flow through singularities is a so-called flow with surgery, so that works assuming either the dimension is 2 or under some more restrictive curvature condition in higher dimensions. So then you can do this flow with surgery that was also done for Ricci flow by Perlman. So the basic idea of this is whenever you hit a singularity, then you actually see some necks, and then you can cut along those necks and glue in some caps and continue the flow of the pieces. So that's a more controlled way to flow through singularities. Good. Okay, so this theory in the mean convex case that was developed over the last 20 years by Brian White and Huisken in Australia and Brendle Huisken and myself and Kleine.
I have a question.
Sure.
Is it understood that the flow with surgery will tend to the same thing as the weak solution, or is it really a
yeah, that's a good question. So this flow with surgery depends on some parameters. So you have to pick some parameter like let's say the neck radius of at which scale you actually do the surgeries. And then if you look at the sequence of flows with surgery, where this neck parameter, this neck radius goes to 0, then it converges to this unique weak solution.
Great, thank you.
Good. Okay, so the big picture is in this mean convex case, we have a very precise theory. But on the other hand, if we don't assume anything about the sign of the curvature, then the flow is much less understood. And to some extent, that's a feature of the equation. So there's some example by Angen and Chop-Illmannen from the 90s, which looks as follows. So there's an example of a surface. It's asymptotically conical, and it has some higher genus. It actually has 4 handles here. And at the surface, if you flow it, it just shrinks in a self-similar way. And then it forms this conical singularity. And if you have this conical singularity, then this causes non-uniqueness. So out of this conical singularity, one can flow out in more than one way, even topologically. So you can either flow out in this connected way, or you can flow out in this disconnected way. Yeah. Okay, so the general fact of life is those conical singularities, they cause non-uniqueness. So that's shown by this example from the 90s, and it actually can also be observed even experimentally. So there's some experiments. So you have some water and oil. So the gray stuff in the background is oil, and then the sphere here is water, and the black ocean is also water. And there's some electric field which lets you bring the sphere close to the water, and then at the moment when they meet, it's modeled well by a cone, and the evolution is modeled well by mean curvature flow, because mean curvature flow is the most efficient way to decrease area. And then it can either happen that those 2 pieces of water combine into one piece, so that would be like this picture, or it can happen that it bounces off again. that would correspond to the second picture here. Okay, so this non-uniqueness is really a fact of nature, and it was even published in Nature.
I'm sorry, I have a naive question. Do we know what other parameter determines which of these two solutions will occur?
Yeah, right. So yeah, I cheated a bit for the purpose of the talk. So actually, when you really do the experiment, what matters is the cone angle. So there's some critical cone angle. So by changing the strength of the electric field, you can change the cone angle where they meet. And depending whether that cone angle is above or below some certain threshold, either this combining or this bouncing off will be energetically favorable. So in that case, there is some selection mechanism which is based on which one decreases energy faster. But in general, it's just highly non-unique, and it's a very much open problem. Well, is there any way to select the best solution, or are they all equally good?
Thanks, that's very honest cheating.
Good. Okay. Good. So the picture as well, this mean convex case is very well understood, but on the other hand, the case without sign for the mean curvature is that there's no theory at all, essentially. And so then the main conjecture to decrease the gap between the good theory in the mean convex case and the non-existent theory in the general case was the so-called mean convex neighborhood conjecture. So the conjecture says if the singularity is nice, meaning if the singularity is just a neck singularity, those conical singularities were complicated. They caused all kinds of troubles like non-uniqueness. But if we assume the singularity is nice, the singularity is just a neck, then the conjecture is then there should be some space-time neighborhood of the singularity of positive size where the flow is mean convex, where the mean curvature has a sign. Okay, so here the difficulty is somehow one has some I will explain this in more detail later, but one has some infinitesimal assumption, one assumes the tangent flow is a cylinder, but then one wants to get some macroscopic conclusion about the sign of the curvature in a neighborhood of some space-time neighborhood of some positive size epsilon. Good, okay. Another conjecture is the uniqueness conjecture. So we've seen the flows through conical singularities can be non-unique, but it's also been conjectured in the 90s that the flows through neck singularities should be unique. And another related conjecture is the two-sphere conjecture. So mean curvature flow of embedded two spheres should be well posed. So if you remember this example for non-uniqueness, that actually was a surface with positive genus. So the conjecture is with genus 0, those conical singularities cannot happen. Good. Okay, and maybe just as a side remark, so two-dimensional spheres sounds kind of innocent, but actually it's a very hard problem. So if you compare mean curvature flow with Ricci flow, then you have to multiply the dimension by 2. And I hope we all agree that 4-dimensional Ricci flow is very difficult. Okay, questions about the statement of those conjectures? Oh, there's another one. There's also the multiplicity one conjecture. So maybe I don't go into that, but just for the experts. So when one takes some limits, then really one does it in some geometric measure theory sense. And in particular, those limits could have multiplicity. So you could have things like two planes connected by some small neck, and then in the limit you just get this plane, but not with multiplicity 1, but with multiplicity 2. Good. Okay, so let me explain a bit more what those conjectures say exactly. So let's take some mean curvature flow of surfaces, and then given any point x0, t0 in space-time, and any sequence of rescaling factors lambda I going to infinity, we can look at the so-called tangent flow at x0. So you just take the flow and declare x0 should be your new center point, your new origin. So you just first shift x0 to the origin, and then you parabolically rescale by those dilation factors lambda. So you rescale space by lambda and time by lambda squared. And then you pass the limit where those rescaling factors go to infinity, and then you get some limit, and any such limit is called a tangent flow. So those tangent flows, they're always self-similarly shrinking. So that's a consequence of some monotonicity formula. And one of the simplest examples is if you look at this neck-singularity, like the picture from the beginning of the talk. If you look at this point where the neck-singularity forms and look at the tangent flow, then you see a round shrinking cylinder. Okay, well, there's some ODE for the radius, which tells you the radius must be this prefactor times the square root of time. Okay, so neck-singularity is a singularity where the tangent flow is this shrinking cylinder. So in dimension 2, that would just be S1 times R. Good. Okay, any questions? Good. Okay, so then some of those conjectures become theorems. So the main thing we proved was the mean convex neighborhood conjecture. So in dimension 2, that's joint work with Keonsa, Choi, and or Hershkovitz, and in higher dimensions, Brian White helped us also. So we proved if the mean curvature flow has any neck singularity, then the flow is indeed mean convex in the space-time neighborhood of some positive size epsilon. And then we also proved the uniqueness theorem. So we proved, we saw in examples conical singularities can cause non-uniqueness, but we've proved that if all singularities are of neck type, then the flow is unique. And then we proved the sphere theorem modulo the multiplicity one conjecture. So assuming the multiplicity one conjecture, mean curvature flow of embedded two spheres is unique. Okay, so existence was already known, and once you have uniqueness, it also depends continuously on the initial data. Good. Okay, and the multiplicity one is still one of the main open problems in the field. Good. So let me tell you how those conjectures are related to each other. So the main thing was to prove the mean convex neighborhood conjecture. Then those other things, they followed from prior results. So let's see. So that's quite easy. So if you have a mean convex flow, then this flow is moving in one direction. So then it was known since the 90s that if a flow is mean convex, then it's actually unique. Because, well, if you just move in one direction, there's no source for non-uniqueness. And then more recently, this was localized in a nice paper by Hershkovitz and White. And so their assumption is exactly what the mean convex neighborhood theorem gives us. So therefore, mean convex neighborhoods imply uniqueness. And then for this other implication, so if you remember before this example of this asymptotically conical shrinking surface, this had positive genus. And actually Brendle proved that's always the case. So if you have a genus 0 surface, if you like the sphere or the cylinder, then the sphere and the cylinder are actually the only self-similarly shrinking solutions. And that's why the uniqueness conjecture implies the sphere conjecture. Okay. So those conjectures are all related to each other. So the thing we really had to prove was the mean convex neighborhood conjecture. So let me tell you why is that a difficult conjecture. So in the first slide, I showed you this nice example of this non-degenerate neck pinch. But then there's a more nasty example, which is the so-called degenerate neck pinch. So you can think like you have your dumbbell with those two spheres and the neck in between pinching off. But then you can modify your example. You can make one of the spheres smaller. If you make one of the spheres very small, then it just moves through the neck before the neck pinches off and you don't have a singularity at all. And if you make it large, then you have the standard neck pinch example. But then there's a borderline case in between where the sphere moves through the neck at exactly the same time when the neck pinches off. And that's called the degenerate neck pinch. And so that one of the main enemies in proving the mean convex neighborhood conjecture would be this potential scenario of a degenerate neck pinch with a non-convex cap. So you worry that, well, you have this neck pinching off, but then you worry that if you look at it under the microscope, it might look like this. So here you see your cylindrical neck, but here you might have this cap which is not convex. So that's kind of the main enemy. And so the issue is that the tangent flow doesn't capture the whole singularity. So when you look at the tangent flow, you always just see the round shrinking cylinder. You just see what's going on asymptotically over here, but you never see the cap. Right. So that's one thing you should all learn from today's talk. So what is the difference between a tangent flow and a limit flow? So remember, for those tangent flows, we looked at the flow around some fixed point x0 in space-time and rescaled them past the limit. And those guys are always self-similarly shrinking. But more generally, you could have any sequence of points xi and rescale around the sequence of points xi. Then you would get some more general limiting object called a limit flow. So for example, here to capture the cap, you wouldn't rescale around some fixed point in space-time, but you would rescale around the sequence of points which follows the tip of your cap. And then you would actually see that limiting object. And so those tangent flows, when you rescale around some fixed point, they are always self-similarly shrinking. But about those limit flows, we know much less. So those limit flows there's no reason why any limit flow should be self-similar. Good. So the only thing we know about those limit flows is that they are ancient asymptotically cylindrical flows. So ancient means they are defined from time minus infinity on. So that's kind of obvious because, well, we took this flow and we rescaled it by a sequence of factors going to infinity. So then the sequence is defined on longer and longer time intervals. So then the limit is defined all the way, starting from time minus infinity. And well, if we rescale suitably, then we can still see the cylinder somewhere. Now, instead of as blow up, as blow down for time going to minus infinity. And finally, it's some flow in some weak technical sense. So those limits are possibly singular, but let's not worry about that. Okay, so let me give you some examples of ancient asymptotically cylindrical flows. So the easiest example is a round shrinking cylinder. So this round shrinking cylinder, well, it existed since forever and it just shrinks self-similarly, and well, it's just a cylinder. So in particular, it's asymptotic to a cylinder. Good. Maybe a more interesting example of an ancient asymptotically cylindrical flow is this translating ball soliton. So that's what you see in the example of the rotationally symmetric degenerate neck pinch. So that's how the cap would look like. So that's a solution of the mean curvature flow. It's also self-similar, but not shrinking, but translating. So in the mean curvature flow, that whole thing just translates with constant speed. So it doesn't change its shape, it only changes the position. And so it moves this way when you go forward in time, When you go backward in time, well, it would move this way. So if you go backward in time, then you would see again this asymptotic cylinder here. So for very negative times, you again see a cylinder, so it's indeed a asymptotically cylindrical flow. Okay. Then there's a third example, which is in a sense more interesting because it's not self-similar. So that's the so-called ancient ovals. So there's an example of an ancient solution, which forward in time it becomes a round sphere, but if you go back in time, it becomes more and more oval. So it kind of looks like two translating ball solitons glued together along a long neck. And again, going back in time to infinity, you see this cylinder here. So it's another example of an ancient asymptotically cylindrical flow. The main theorem we proved is, in fact, that's all. So if you give me any ancient asymptotically cylindrical flow, then I tell you, well, it in fact must be one of those three examples. So a real main theorem is a classification result for those ancient asymptotically cylindrical flows. And so in particular, just by inspection, all those three examples are convex. So therefore, the mean convex neighborhood theorem follows from the classification theorem. So just by a short argument by contradiction. So suppose the mean convex neighborhood conjecture was not true, well, then you have a sequence of nearby points where the mean curvature changes the sign, but then you blow up around those points and pass the limit, then you see one of those three guys by our classification result. So but then what you see actually is convex. So after all, the mean curvature didn't change the sign. Good. Yeah. Was there a question? Maybe not. Okay. So let me just mention, of course, there's a lot of important other prior work and classification. So somehow the answer is always the same. So the answer is always one of those guys, but the assumptions are different. So there's a early pioneering work by Shusha Wang. So he assumed it's convex and self-similar translating and an entire graph and two-dimensional. Then he proved it's a ball soliton. So then I proved again kind of the same, but in a more geometric setting and also in higher dimensions. So then there was a nice paper by Bernstein Wang. So the cool thing about their paper is they didn't assume convexity anymore. And then there was a recent breakthrough by Brendle Choi and Angenem Daskalopoulos Sesum. Well, they still assumed quite many things, but the breakthrough was that they didn't assume anymore that their solution is self-similar. So,
Robert?
Yeah.
I believe there is a question by your colleague, Balind Virag.
Go ahead, Balind.
Oh, yeah, no, it's just so when you talk about these three options, are these just exactly one solution each, or are they just classes of solutions that you have?
Essentially, it's just one up to silly things. I mean, you can have a bowl and just shift the origin somewhere else, and so up to rigid motion. And
what is the equation for those shapes? Is that something simple, or is it?
I mean, the cylinder is explicit. So for the oval, it's given by some solution like of some ODE. So it opens up like a parabola, but it's not really an explicit formula. And yeah, for those ovals, there's no explicit formula. And yeah.
Thanks.
And so the ovals, they are really a one parameter family. There you also have some. So they are unique up to rigid motion and parabolic rescaling. Good. Okay, so usually when people classify stuff, well, they assume either it's convex or it's self-similar. that makes it kind of easier to classify things. And so the reason why I really like our own classification theorem, because I think that was the first time where we succeeded to classify something, assuming neither that it's self-similar nor that it's convex. And of course, that's absolutely crucial for the proof of the mean convex neighborhood conjecture, because convexity is what we want to prove, not what we want to assume. And also, self-similarity is something we can't assume because we want to look at any blow-up limit, not just at tangent flows. Yeah, so that's what distinguishes our classification result from all those prior results, that we assume neither self-similarity nor convexity. And that was the key for the proof of the mean convex neighborhood conjecture. Okay, so it's a colloquium, so I just skipped the idea of the proof. So maybe let me mention in the higher dimensional case, we also developed some new methods. So there's this classical moving plane method, which is used all over in PDN geometry to prove symmetry. So that's originally due to Alexandre, who proved that soap bubbles are always round. And then it was also used by Sarah Nierenberg and so on in the PD setting. And so the moving plane principle roughly tells you, well, symmetry at infinity or symmetry at the boundary can be promoted to symmetry in the interior. And so the new principle we established is, well, classically one works with smooth objects, but the new principle we established is actually that both smoothness and symmetry at infinity can be promoted to smoothness and symmetry in the interior. So we have some method where one can not just derive symmetry, but symmetry and smoothness, and it's important that we get both of those things in tandem simultaneously. So that's kind of the picture. So somewhere in the proof we understand the asymptotics very well, and then we use this new moving plane principle but a priori this cap region could have spikes, but then we use the moving plane principle to prove actually this whole solution is symmetric and smooth. And then we are done. Then it must be one of the few examples. Okay, good. So I think I stop here. We have some time for questions.
Okay, thank you very, very much for beautiful talk. Pure colloquium, so I really appreciate it. I think I'm not the only one. Actually, almost everyone stayed up to the end, which is amazing. So, are there any questions or comments to Robert?
I have a question. Can you hear me?
Sure.
Perhaps you've already answered this question, but you presented results from two teams, for n equals 2 and for n bigger than 2. Is there a basic reason for this?
Yeah, so one of the main differences is this moving plane thing that I mentioned. So in the two-dimensional case, we can actually prove some estimate which tells us the whole solution is smooth, and there are no, we can prove that there are no singularities. And in higher dimensions, that's more difficult. So in higher dimensions, we have this extra step with this new moving plane method where Brian had a good idea, so he joined us for that.
Thank you.
Sure.
I had a question.
Mm-hmm.
So you said that if you have a certain barbell, then you end up with 2 round points, right?
Yeah.
Is there a way to make that into a theorem? That if you have, something you specify an object is like a barbell with some kind of isoperimetric inequality, then you have more than one limit point?
I mean, one can prove things like, well, if one has this neck pinch singularity, and if one perturbs the initial surface, then one still will encounter a neck pinch singularity. But I'm not sure if that's what you're asking. But yeah, even in this mean convex case, so that, there's still many open questions. For example, it's unknown if the number of singular times is always finite or not. So yeah, you could potentially nobody knows how to exclude that you have like a Cantor set of neck-pinch singularities.
May I ask a question?
Sure.
Sure. I know that another way of formulating the mean curvature flow is the more PDE, the level set method.
Yes.
And I'm curious, in the case of a conical singularity, do you know, in the non-unique conical singularity, what is happening to the level set flow there? Because you can always define it, but sometimes it goes haywire and stops telling you stuff.
Yeah. Yeah. So I mean, the level set flow is unique by definition. So
yes.
So right. So but for level set flow, the right way to talk about non-uniqueness is to talk. So if the flow is non-unique, then the level set flow is fattening. So it forms some interior.
So this would be a case where you develop.
Yeah. So that would be the outermost solution, and that would be the innermost solution, and the level set flow would be everything in between.
Oh, so it kind of envelopes all the possibilities.
Yes, right.
Thank
yeah,
you.
so those two are in some sense the best two solutions because it's the outermost and the innermost solution, but then there are many other solutions in between.
Okay, thank you.
Sure.
I have also, again, a naive question. Are there any other known quantities that are monotonous under this flow?
Not that much, because if you look at the evolution equation for the curvature, it's a rather boring equation. So what is preserved is, so convexity is preserved and mean convexity is preserved, and then there are those conditions in between that are also preserved. K convexity, meaning that the sum of the K smallest principal curvatures is positive. And that's it, I believe.
Okay, thank you.
Other questions or comments? So I don't think there are other questions. It's a good timing to finish. We're 3 minutes past the hour. Well, I would, in the name of the CRM and the whole Canadian community, Robert, I would like once again to congratulate you for this outstanding achievement. It was a pleasure to have you today giving a talk in the Colloque des sciences mathématiques du Québec. And I would invite all of you to actually join us in a couple of weeks to see the lecture of Egor Shelukin from Université de Montréal, who is the other recipient of this year's prize. And okay, so thanks a lot once more, Robert, and see you all.